Business process modeling is a powerful technique for graphically or digitally representing a business's processes or workflows as a model. And now with Hash, you can take these models, draw them in Hash, and simulate them, automatically exploring how they perform under different conditions with different parameters in different contexts. No coding required. In this tutorial, I'm going to walk through using Hash's process chart, a visual interface for creating business process models within Hash. We'll take a hypothetical business's process, represent it in Hash using this visual interface, simulate it, and then create an experiment to see what happens when we have different parameters for this model. Let's say that we work in a widget factory and people really like our product. They love it. For the most part, no problems. But occasionally they have a problem or they don't understand how to do something. And when that happens, they generate a ticket. That could be an email, it could be a phone call, anything that's going to send something to our employees who enjoy answering these questions. Now, the process we need to figure out is what's the best way of handling the tickets that come in and getting them to the employees. We could have them automatically go to each one. We could have them be prioritized based on the type of employee who's going to answer the question. A lot of different ways, but I recommend that we start off by using some type of queue. Standard data structure for this kind of system where tickets will come in, they'll be added to a shared queue, and employees will be able to pick them up from the shared queue. So we can make some connections here between them, and when a ticket comes in, it gets added to the top of the queue, and then when an employee has solved it, it'll leave, or an employee will pick it up from the bottom of the queue, work to solve it, and then when it's actually solved, we'll want to collect it somewhere. So the general process looks like this. Employees pick up the oldest ticket from the bottom of the queue. They work on it for a little bit. Maybe I can express that as like an arrow connection to self here. And then when the ticket has been solved, it'll be collected somewhere. So we'll call this our sync. And this gives a basic idea of how we want to model the process. Now let's convert this diagram into a Hash simulation using the Hash visual interface for building process models. So now that we have a good idea of what the process model is that we want to represent in Hash, let's go about doing it. Let's create it. And to start, we can do that by visiting the Process Chart tab. And you can get there by clicking up here or by going to View Process Chart. And what you'll immediately see is a node and wire style interface for creating blocks and connecting them together. And this is how we're going to visually represent the process chart that we just drew in our diagram. This is how we're going to represent it for Hash. And then we can add it to the model and we'll have a simulatable process model ready to go. So on the left-hand side, you'll see some ways of moving around and navigating the process chart interface, a tool for connecting nodes together, and then different blocks. These are the nodes in the interface that represent the different elements of a process model, the different kinds of behaviors that we can have that will represent different parts of a process model. And I'm going to walk through some of them, and then we'll pick a few that will match up well to the logic that we described for our business process. So to start, let's look at this start node, and this is going to be available in every one that you actually start out with, and it's a source block. So a source block generates the objects that are sent through a process model. In our case, it'll be tickets. So these are going to be the tickets that are going to be generated and that are going to be sent in by our imaginary customers. So I'm going to rename this generate tickets because that's what it's going to do. And then we want to send the tickets to our employees. Now, there are a couple of different blocks here we could select. And don't worry about memorizing all of these. You can always look in our docs to learn more about what each process block does. For this simulation, I'm going to jump right to the service block. It's a really common block because it performs a really useful function. It's going to represent employees. Well, in our case, it's going to represent employees taking tickets, working on them, and solving them. In general, what it represents is some kind of resource being seized, held for a certain number of time steps, and then released. So that can apply to a wide number of process models. And for ours, I'm just going to call this solving tickets, and we'll get into the individual parameters in a moment. And then we're gonna end our process model with a sync block. And this is the block that accepts objects and closes them out. It's kind of like you are finished up with the tickets, and this is where we'll count, collect them, and end the process. So I'll record some metrics here as well, and I'll call this finished tickets. Now let's connect them all together. And boom, we have a very simple process where tickets are generated, they're sent to our solve tickets queue, and we'll have some employees work on them, and then after a certain amount of time, they'll finish, and they will send them to finished tickets. Now we can get into the logic of each block. Let's add parameters to them. And the business logic is where we add the, well, let's say interesting parts, the data for the process model that's going to make it reflect your own process. And again, you can learn more about what each block's parameters are by just clicking on that question mark or navigating to our docs, and we have descriptions here. I'll walk through them though for the ones we're going to use for this model. And really, it's let's start out with the source block. You're always going to have a template for the objects. So this is going to be a JSON dictionary that is the representation of the object that is sent through the process model. For our process model, we really don't need anything more than this. This is all that we need because we're not adding any special data. We don't have any kind of parameters really for the tickets yet. But just kind of looking forward, I'm going to add a property to tickets that we'll call priority. And this will either be true or false. For now, all of them will just be false, but you can definitely see how a ticket process model might want to have some concept of priority. Maybe some tickets they send in are high priority, and we want to route those to different people. That's a direction that we could take our process model, but we probably won't get into right now. The other thing I want to describe on the source block is the frequency or the rate parameters. These are the parameters for source that determine how frequently and how many objects are produced by the process model. And frequency is a little subtle. What this is saying is on which time steps should I produce an object? If it's 1, then it's going to produce an object every time step. If it's 2, it'll produce it every other. If it's 3, every third, and so on and so forth. And then rate is asking when it produces, how many should it produce? So if we just set this as 2, then every time step, it's going to produce 2 objects, in our case 2 tickets. And if we don't set frequency, it just defaults to 1. What's important when deciding what these parameters should be for a process model is you have some conception of how real-world time maps to model time. This is important in a lot of hash simulations, so it's worth kind of going a little bit into. You need to be thinking about how, when you're making a simulation, how certain properties parameters are going to map to the real world. Like in this case, if I know that I'm getting 2 tickets on average into my support queue every 5 minutes, then maybe I want a time step to represent 5 minutes. And so I'll just leave this as 2. That means we're going to get 2 tickets in every time step. And since we think it's going to be, kind of scrolled over there. So we're going to get 2 tickets every time step. And then we'll want to keep in mind the time step represents 5 minutes. So when we set other properties in the future, we can rationalize it to that. And whenever I set time steps like this, whenever I have this kind of assumption or this link between the time step and real world time, I like to add it to the README doc so that I remember that 1 time step is equivalent to 5 minutes. And now when we set future properties, we'll want to keep that in mind. So that's about it for our source block. There's more that we could add to it. And again, check out the docs to learn more about it. But let's look at our solving tickets block. Now, in this case, we got a number of different properties for the service block. And I'm actually going to jump to the resource property because this is one that you're going to need for every one of your service blocks and for a lot of other ones. And the resource property is it's a global property on the process model. It's one that other blocks can reference and use. And for this particular process model, we're going to call it employees. Could be anything. Maybe you're making a pizza simulation and you have a limited number of ovens. Then you could have ovens as the resource. But in this case, it's employees. It's our employees who are solving tickets, who love to solve tickets. And we got 3 of them, and they are ready and willing to go. And so once I've set it, which again is by clicking on this gear icon, I'm going to go back to solving tickets. And I will select employees. That's going to be the resource that this service block uses. Now we want to set the amount of time it takes for an employee to solve a ticket. And this is where you should be thinking a little bit about the process that you want to model. Like, what is it in the real world? How long do I expect a single ticket to take an employee to model? And there's some ways that we can introduce stochasticity and differences for tickets. For instance, we could use uniform time or a triangular time. Those are uniform distributions and triangular distributions to generate the time for each individual ticket, representing the kind of randomness that might happen. But for now, let's just say that it's going to take our employees, on average, about 10 minutes, 2 time steps to solve a ticket. And we'll leave that there. And again, there are other properties you can set, but this is a good start. And now if I go over to the sync block, nothing else we need to set. We've got everything here. Sync is easy. We just really need a name and to check which of the metrics we want to record for it. So that's about it for our process model, for creating it in this visual interface. I'm going to give it a name, customer service. And now I can add it to the simulation. If I had an existing model, which we'll see in a second, I could select that and cause it to update it. But since this is the first one that we're creating for this simulation, this is the only option, which is to add it to the model. And if I do that, I forgot. We're not recording times here, which we can. I'm just going to unclick this, though. Let's just keep this simple, do that, and let's try that again. And there we go. Create customer service.js. So it's creating the process that we've defined here. I'll walk through a little bit about what's happening with the files that we've added. So as you probably recall, hash simulations all start off in init.json, where you have an agent that runs a behavior. And this single agent is running a single behavior, create customer service.js. That's the behavior that was generated by the process model. And what this behavior is now doing is it's taking all of the parameters that we defined here, and it's taking the order of behaviors, order of process model blocks, and it's representing it in a single agent called customer service. And it's got the relevant behaviors here, the ones we've defined, along with some that you just see in every process model. And it's going to execute those every time step with the parameters that we've set. So now, if I want to run my process model, I can do that. I'm going to just reset the simulation here. And you can see in raw output that it starts off with the agent that was set in init.json, which is going to run this create customer service behavior. And now we can step through our simulation. And it's not too exciting what's happening yet. You can't really see, but we've got this queue full of different tickets that are coming in, and employees are being assigned to deal with them. And as they deal with them, they slowly solve them and decrease the amount of tickets in the queue at any one time. We've got a bunch of different charts here that are going to describe what's going on. Here's a few area ones that count the number of total finished tickets. Here's one that's going to look at the number of finished tickets on a particular time step. So all really useful metrics for understanding your process simulation. The 3D viewer isn't going to be too exciting because it's all happening on this one agent, but you can see that we've initialized it. You can check out the behaviors for the process simulation, all the different properties we've been talking about. The solving tickets queue is the currently active queue. And yes, that's a good starting place to see how to define a process chart and represent it within a simulation. If you want to update your process model, you can do so by revisiting the process chart. Well, you can do it in two ways. One, you can manually edit the logic here, or we can go back here and change the details. So now we want to make sure that we're on the right one. We could create a new process, so we could have multiple processes in a simulation, but we're just going to update customer service. And yeah, now you can have an updated create customer service behavior as well. If we want to, so one, this is just a great starting place. Once you've got this, you can play around with different properties, different parameters, and see what is a ideal number of maybe employees, for instance, to handle and manage your ticketing queue. Once you've got a handle on that, we can go a little bit further and start creating some experiments to explore across a range of parameters what is the best ones for a given process model. So I'm going to show a real simple experiment here. Again, let's see number of employees. And to do that, I'm going to add a global property, num employees. So I'm calling that from context, calling globals. And when I switch over to globals, I'll add num employees. So let's keep the number that we started with, 3. But then also, we're going to create an experiment. Let's just do value sweeping to just show a simple one to start. Or actually, I think linspace, a linear sweep is kind of cool. So just like that, start 1. So that's going to start at the range of 1, let's say 10, and let's just take 9 samples. Call this sweep number of employees. So now when I run this experiment, it'll sweep over the range that I've defined here. And I'm always terrible at math. I'm not sure if it will actually, maybe it'll give us a float given 9 samples. So I'm just going to add a floor here. And yeah, now if I run this, let's see what happens. Oh, I hid the view. of our experiments. I can switch back here, or I could have done view hide activity to show it again. But now we can check into each of our runs, and see, all right, here's it with that number. Now if I flip over to analysis, we can see it's much smoother. It seems like they're not quite as well utilized as if we had like 2 employees, which makes sense. So that's the process modeling and process chart interface. Play around with it, try simulating your own process charts, and let us know how it goes for you. If you have any questions, you can ask in Slack or send us an email. And good luck and have fun building your process models in Hash.